Thirayut, yes, and last name Lau Kun San, and is responsible for is a manager for RF microwave in a section in my RF microwave.
So we are in charge of realizing the second for the Switzerland, and we have all the facilities for the calibration related to time and frequency here in Switzerland. And if you have an interest on that, we can take a look at the laboratories today to give you a better feeling about what we can do in that field.
Okay. My name is Marc Olivier. André is my last name, and I'm in charge of the sector electricity, where two labs, RF and microwave and EMC, are located.
Now, maybe you have something to add to that afterwards, but I guess after that, you know, there is actually the possibility to visit 3 labs. I don't know, are you interested in all of the 3 labs to visit, or, I mean, is it okay like we wrote it down here, or do you have any other preferences? I mean, the lab visits, you know, EMC lab, RF and microwave lab, time and frequency, is that okay?
Okay.
For you?
Yeah.
Enough? Is it enough?
Oh, enough. Very good.
Yeah?
Yeah. Okay.
Anything else you would like to discuss? Something specifically?
A broad introduction to our institute, and you will see that there are some similarities to the NIMTI, Thailand Institute. So I will start with a short movie about metrology, which is without words, but you will understand. There should be some music.
Oui, accéléré là.
No. It's about the measurements that we do here at METAS. Chemistry, as you can see. Measurement of big volumes, electric power, electric fields, speed, electric fields here, EMC. EMC lab, you will see later. Dimension. We have a strong group in dimensional measurements with 3D machines, very high level 3D machines. We also support activities for industry, also for legal metrology, control in the market, also a strong expertise in mass. These are mass standards, national mass standards, with very high level accuracy and uncertainty levels. And if you like, all basic or derived units are controlled here. Not all that exist, but most of them. This is a small movie, normally with some music, but not this time. I don't know why. Okay, so maybe we can continue with the presentation. Is it okay with the light, or you have enough light? Yeah. Okay. Metrology. It's an old history. Everybody wants to be sure that he pays for the right amount. You want the right amount, the right quantity. For gas or for the supermarket, if you buy vegetables, it needs to be correct weight. So this is the history of metrology in support to the population, to the society. There are some more modern issues like radiation. Are we sufficiently protected from radiation sources in hospitals, around nuclear power plants. This is also metrology. Or climate evolution. We measure the temperature very precisely all around the world to be sure that we understand how the climate is evolving. Also, science is linked with metrology. Science progresses thanks to metrology, and metrology progresses thanks to science. There is an interconnection. And also industry, innovation. We want to give our industry a good competitiveness, a good quality level. Probably you have the same expectations in Thailand. If you want to be competitive and with high quality, then metrology is needed. You can see in this example, if you want to build a complex reactor or even more, a complete airplane, with a supply chain around the world, everybody needs to be on the same measurement basis. Otherwise, you cannot put such a complex system together. There is a need to have all the same foundation, the same basic foundation, so that 1 millimeter in Switzerland is 1 millimeter in Thailand, in China, in the United States. The same for all units. There is also the need to be sure that we also protect the population correctly. When I measure radiation doses, it needs to be exactly the right value. Otherwise, it can be life-threatening, or it cannot do the treatment it is supposed to do. So we want to be sure that the radiation measurement devices in the hospital are correctly calibrated. And you want them to be calibrated to the best standard in the country or in the world. So if I undergo a treatment in Switzerland or in Thailand, I want to receive the same doses. It's very important. So calibration, traceability to the top level standard. What are our missions? We support fundamental metrology. We contribute to time. UTC Switzerland is made by Jacques. You have Mr. UTC Switzerland here. We deliver services to the industry. Services like to your industry, airline industry, air control industry, for example. We also carry out research and development activities. We support our colleagues from legal metrology, and we are also representing Switzerland in the international organizations, BIPM in Paris, as you know. Fundamental metrology. We do maintenance of the national standards. Here an example of mass, or meter, or volt, or ohm. All these units are maintained here at METAS for Switzerland. But Switzerland is not alone in the world. So we need to compare our standards with our colleagues in other countries, in Germany, England, France. So our best standards are compared against the best standards of other countries. Probably Thailand, for sure Thailand does the same in the Asian region. And also, we work to the evolution of the metrology system. As you know, today we have 7 basic units, kilogram, meter, second, etc. Next year, there will be a big change. We will not have any more 7 units. We will have 7 basic constants. Like, for example, the speed of light. The meter will not be anymore a basic unit. The meter will be replaced in the definitions by the speed of light. The ampere as a basic unit will be replaced by the charge of the electron. So it is a change in the concept. It will not change anything in everyday life. But the basic units will be gone. They will be replaced by basic constants. Okay? We realize UTC-CH. We have 5 or 6 atomic clocks that you can see when you visit Jacques' lab. Every day, we're constantly working, making an average for UTC Switzerland, doing a daily comparison with Germany, correct? Or another country as well.
Basically, we are comparing with every other kind of realization.
Okay. But every day with Germany, is that right?
It's continuously done over the 2 days with all contributing laboratories.
Not only Germany. Okay. So,
A common view. Common view.
It's
Technique.
a two-way.
Two-way common view. Oh.
you can see on the diagram, back and forth,
Oh.
through a satellite link.
Oh, something like that.
What do we deliver as a service to the industry? The basic service is calibrations, top-level calibration. Hopefully we can deliver some to your company, but we deliver to many other companies. Bordeaux Strats is a customer, Keysight is a customer. In high frequency, in EMC, we do a lot of antenna, complex antenna calibrations. So this is our historical service to the industry. But we also do more and more tests or measurements for certifications or for companies that require a good metrological support. I would say better than average. We also give consulting or expertise. Sometimes there are some very tricky issues, like measuring fields of telecom antennas, 4G or 5G. Here we develop also expertise to support the telecom operators, for example. And finally, we are a company like any other. People are not, for the commercial activities, people are not obliged to come to us. They come to us if they recognize that we have a superior service. And we try to provide a constantly superior service. You understand? A company can calibrate something in a calibration lab. If it is a meter or if it is a kilogram, others can do it. If it is a top-level meter, top-level kilogram, we try to do it. We also do research and development. We carry out scientific investigations. Here is a top-level mass comparator in vacuum to be sure that there is no influence of humidity, of buoyancy. So this is an example of a nice machine that was developed and improved here. We do usual developments and improvements about new technologies. We know.
Hello.
No problem. We know that technology progresses and we try to keep ourselves at the top level as much as we can. Legal metrology. These signs are put on measurement equipment that is supervised by law, like electricity meter, like tank, gas station for petrol for cars. This is on scales, balance, weights in the supermarket. These are all measuring instruments that are controlled by the state. So when the state is controlling a measuring instrument, there is a certification or an approval process. And when this is okay, there is one of these stickers which is put on the device. We do approval, we do conformity assessment. Conformity assessment is, you certainly do the same in Thailand for some activities. And also we verify or control that all the instruments in the market follow the law, that they are correct. It can happen that they are not correct. Maybe you can show them an example. I don't know.
Yes.
We will show you an example of a device from the market that is not correct, not compliant. And this was found here through the surveillance activity of legal metrology. We also represent Switzerland in international organization. BIPM is the top organization in Paris. Euramet is the European organization of the institutes. WellMed is the legal metrology, so in all these international bodies, we have a representative. Sometimes we even have the president of these institutions. So as you can understand, at METAS, we have two main pillars. On the left, this is the legal metrology. We are making sure that the Swiss law is being observed and complied with. On the right-hand side, we have the industrial services, private contacts like with your company, internationally. And everything is linked with a national metrological base, which is here. So we have the top measurement institution, and we have two main activities here. As you understand, in metrology, we try to always become better and better in time. You want to buy the best instruments that are available today. You want Rohde & Schwarz to give you the best possible instruments. In 10 years, you expect Rohde & Schwarz to give you better instruments. So we do the same. We have today the best possible standards, and we want in 10 years' time to give the best possible, better standards. So there is a continuous improvement, okay, progress taking place here in measurement capabilities. Here is our organigram. We have two main organizations. We have physics and chemistry. This is physics and chemistry. Electricity is there. Time is there in four main groups. And here we have legal metrology, everything which is related to law, like writing new law, verifying, surveying, controlling, or doing conformity assessment. Today, you are visiting basically 3 labs, but the original
Ça fait des vibrations et puis ça détecte des petites forces.
สนใจกันเนี่ย
Yes, yes.
How many fluency operation? Ring.
I think 24 giga.
24. Oh.
Ja, så. Wat is het? Wat loopt? 30 giga. 24. Okay.
24 yes. So exactly 24 gigahertz. Yes. But we have also in Switzerland we have 24 and also now more and more laser scanner. Tack, you know, but based on laser. And the laser makes a picture, and then you see the motion of the car. You estimate the speed from the motion of the car. Yes. So we use this chamber for testing. This is the testing activity. You know, we test certification. But we use the chamber also for calibration. We calibrate container. So perhaps I show you our chamber.
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 Yeah.
Oh, big chamber. It's a big chamber.
Size 10 meters. 7 and 7.5.
Über WLAN müssen sie es nicht haben.
Okay, gut, dann müssen wir nicht so schnell denken, das schnell
Oh, die Frage ist nicht, wie kann ich das Foto anschauen von dem?
Now it's
Aber kann das während dem Betrieb nicht?
Lindgren.
Das müsste ich auch mal irgendwie... Vielleicht also am besten während
We
dem
are
Betrieb über
testing
LAN.
radar for vehicles, speed
Das
radar.
LAN-Kabel haben wir da
Car.
irgendwo drinnen.
This is a speed radar for car. Yes. And we are making immunity testing. So from this antenna, this one, we produce radiation on this system.
The radar
Yes.
in the car.
No, this is outside. It's in the street, you know. How do you say? You have car going, and you have to check the speed. 80 kilometer per hour or 100 kilometer per hour. And to check the speed, you have the system. It's on the side of the road.
Oh,
Check.
it's a form police.
Yes, exactly.
Police.
Check the speed.
Check
from
traffic.
I see. Oh, it's a radar.
Yes.
Speed.
And now this.
Doppler chip.
Yes.
Like that.
Exactly.
Like this.
Exactly. This Doppler effect.
Doppler chip.
And to make calibrations in this range. We have a special, I can show you, we have a special amplifier. This is the
Ja, so ist er oben.
special amplifier that we developed from Metas to perform. And we have a special Helmholtz code, you know Helmholtz, to make very strong. Yes. Yes, this is a Metas development. Yes.
What's it class A and B flat?
So
Class
rotate, check the linearity, frequency response, everything. All this we upload. Cannot? Okay. So we have a we can calibrate field probes from basically 10 hertz to 18 gigahertz. So yes. And then isotopy linearity frequency response. We have also, I can show you, the Helmholtz school is here. And we calibrate also in special ranges, for example, 10 kilohertz to 400 kilohertz. Special mask you see here for antenna calibration. We place that in the chamber. This comes on the side. And we have a special system for echo cancellation in the chamber. So we provide really free field antenna facility.
You can check a 3-dimension, 3 axis bicep
Yes.
axis.
Yes. So this is a special calibration. We make calibration of antenna and also calibration of field probe.
Which probe? Okay.
Yes.
For
you
the
know.
his
Yes.
which probe?
Yes. Here you have one
SMF.
field probe. The geometry of a coaxial cable. This is a big coaxial cable.
Oh, big.
You can see this is the shielding,
Shield.
and this is the inner conductor of the cable.
It's a cable. Action from the cable.
It is the same principle.
Principle.
Yes. And on this side you have absorbing elements. Here, absorbers.
Unit and the test.
Huh?
Unit and the test.
Yes.
Device and the test. Device and the test.
Device on the test is here, just here. You can see. You can see here. So we cover the whole range of calibrations. We see field probe calibrations. Also for calibrations, we have this GTM cell. Perhaps you have seen that.
GTM.
Yes.
GTM.
Yes, you know. The GTM here.
GTM.
Yes.
Oh.
Yes. This is very interesting infrastructure.
GTM test.
Yes. So you can take a look. So we have 3 frequency ranges. 3. Yes. With different techniques. Helmholtz, GTM, and chamber.
It's a measure input power is applied and a measure in a switch probe.
Yes.
The switch length the level.
Yes, exactly.
Oh,
Yes.
exactly.
Measure input power and we know the level.
Reading.
Yes. But of course, we make a calibration of the chamber. We have a small model called microtem cell. Yes, smaller. I will show you. So,
The Thailand has is ETF. ETS.
yes.
ETS.
No, this is the wait. I will just switch off. This is MEB. This is MEB. Measuring instruments Berlin.
Oh, measurement.
Now it's Schaffner. Schaffner or Tezek. Tezek. Now the name would be Tezek. But the chamber is ETS. You see the ETS. Yes. This is Schaffner. The chamber is ETS.
Phía này, phía không trên cáiเข้าตรงนี้ใช่มันสายกัดปากแต่จำลองมันสายกัดปากแต่ขนาดใหญ่
Just take care to the cable. Yes,
The cable.
don't work on the cables like this. Yes.
It's on receipt. It's a measurement interference from the UUC.
No,
Okay.
no. It works so. We have amplifiers here, and we put power in the GTM. So power.
Oh.
power ออกไป
Power.
We keep power to
You
UUC.
give power and create a field.
Oh,
The GTM produce TEM.
TEM
TEM, transverse electromagnetic wave.
Oh, it's a high power
Yes.
to the device.
High power to the
To the
device.
device, okay. Oh,
This
it's
is
a monitoring.
this is monitoring. Exactly. Yes.
Mm.
Yes.
Oh.
And this is not normal. A good balance.
Does
not change. This the number keeps the same.
Aber
This is not
hier
good.
is het zo
No good.
goed.
The shielding system is a fail. Shielding.
Yes. Yes.
Shielding.
Something what I want to show you also is something else. This is this suitcase. Sorry.
Check receiver.
Yes. Yes. All that looks good.
It's an all time.
Can is retired.
You?
Yes. I
You work-
test receiver.
You work
Yes,
for
Rotor
Rotor
One.
One.
Yes, we are. Yes, in
Okay.
Thailand and this is second top.
That's 20 years old.
More.
It's
I
a
think
good.
it's more
It's
good.
a strong. Strong.
Yes. Yes.
Yes, we did.
Here
Aber ik
are antennas.
Het is goed voor het
Of
aspect.
iconical referenceantenna from
Gewoon een batterie.
set of reference.
ที่เขาเทสเนี่ยพี่
By
ใช่ไหมใช้อุปกรณ์มัน
Something I want to show you also is this one.
in the supermarket.
Yes, it's more a chemical industry. Yes, you know, it's
High
really
precision.
high precision. Yes. So you put, you know, you see. And now here, this is, you know, a phone. You know, it's the same electronic. Now look at this.
This is jam.
Yes. You see? You see a switch off?
เปลี่ยนเลยถูกแจมนี่ลองดูนี่
แจม
แจม
Yes.
แจม
You see?
อิมมูนิตี้
You see?
เครื่องไว้
The problem. Now, look at this.
Als er wees niks nodig meer.
Ja.
Wat ik inbond.
Yes.
Not
Not good. Not good.
band.
You see, this is not good. You cannot see. No, you don't see. Here, but you don't see. So with this, you can make visible. Here is micro oven. just water.
Water. Probably this.
Absorption, yes, and these are
The heat.
fuels.
อ๋อ the buff
Yes,
หลอด
yes.
ไฟนั่นเอง buff
Yes.
อ่าหลอดไฟ
So now you will see what happens. I feel like kanskje avschalte maken.
ไว้
I
สว่าง
think it's better,
ไว้สว่าง
and you will see now. We have to wait a little.
อ๋อ
You see the lamps.
อ๋อเดี๋ยวแล้ว
So electromagnetic field. You see
Electromagnetic.
the electromagnetic field now.
the method is the heat don't apply the current the method is the heat and the light
Yes.
the concept the filament is the heat โอเค
ก็ใส่หลอดไฟอะไรก็ได้
อ๋อใช่ที่เป็นเหล็กไงเหล็กฮีทมันจะร้อนครับ
เราหลอดที่บ้านเรานี่ลองก็ได้นะ
เห็นไหม
This
ไปไหม
is you can see the field because with normal eye you don't see. So
dangerous
this is a small test. And also here I want to show just something else is interesting is here an antenna. The antenna will radiate in this direction. And to observe we have just this small
the antenna
this is small dipole.
dipole yes small dipole
Yes, just
Good.
that here in between a small lamp.
อ๋อ LED
No,
Yeah,
not LED, just a filament.
Lamp?
Tungsten.
อ๋อ lamp is a filament
Yes.
filament โอเคอ๋อแบบใช้หลอดไฟ
Yes, now you
Oh,
will see the
small.
demonstration. Perhaps switch off the light. Yes, go a little back. Yes. Yeah, you can switch off, Marco.
vertical for light
Oh, you see. You see, you
it's
can
a
see the
wavelength
field.
it's a wavelength
Yes.
Emax and Emin
Yes.
then okay
Now you see.
absorb
Absorption.
power
If I go outside here,
อ๋อ
nothing.
สายลบแมน
If
ล
I
บ
go down, nothing. So I can make also polarization check.
Polarization.
Polarization here, maximum polarization here.
อ๋อไม่
Nothing.
It's a vertical polarization
So, and I can also make the experiment with metal.
and the backdrop
Yes, so this is metal. Metal. Makes a reflection.
reflection
The wave goes like this, comes
is a reflection
comes back.
Great.
So see what happens now. You will see with that.
reflection
Interference.
half wave half wave
Yes, half wave. So here, 1 point,
every half wave
5 centimeters.
5 centimeters
5
So
centimeters
wavelength is 10.
oh wavelength 5 centimeters
Yes.
what is the power
Is I think 400 watt.
400
Watt.
Geblokkeerd
Ja,
met dat zo dan.
ja, is hij vettig. So. Calculation of power terms. All infrastructure including coupling lines, decoupling lines, all
yes the electrostatic discharge gun
This is to calibrate.
to calibrate
Yes.
from the generator receiver to the measure
No, this is calibration only of the gun.
The gun.
No, the target. The target. We have to calibrate the target. I think we have one here. I don't know.
Arrow shot ทั้งหมดเลยเนี่ยดูวันนี้แหละโอเค
Yes.
อ๋อลิติดกัน
Yes, yes.
ลิติดกัน
Yes.
is insert to the receive for measurement
Yes. So you go to the step. So you can have this device, make proficiency testing in your lab, comes back, and we can see if you did it.
Yes. So you're also calibrating those?
Okay. So this is for this is CNC partner, and we have a test also. Test for automotive first.
Modulate time. Oh, it's the same decision.
Huh?
Same.
Yes, yes, it's the same. Yes.
Oh, I see.
Yes. And this is same test for automotive first.
Yes, so this is the RF microwave laboratory. And we are, I mean, we are doing different things, you know, we are doing calibrations, but we also do a lot of R&D research. So both calibrations
Research
and also research.
and development.
And for calibrations, we, you know, the fundamental quantities in RF and microwave are scattering parameters,
S parameter.
S parameters, and power. And we do both. And here you see, this is the area where we do S parameter measurements. So you can see we have different vector network analysis. Do you have vector network analysis?
I have Roger one. Yeah, 24 particular.
So this is 67 gigahertz metrology option. So it means it has special stability, low drift, good linearity. This is overall the new packet 8510. We don't use it anymore. We have here 50 gigahertz with 4 ports.
4 point. Yeah. You have calibration.
You already sent it to somebody?
Yes, of course. Yes, we have some demand starting at the moment,
Okay.
but we would like to really start to organize. We can do it on bilateral basis for someone who wants a quick check, and we have some demand starting, and we would like to do it on an international comparison. Perhaps the motivation of labs to participate is bigger. If you have, say, 20 labs. Yes. So.
Do you have any questions?
No.
Just ourselves. We are the big specialists. Yes, we are the best, actually. So for S parameters, we have the highest level in the world. Yeah. Because, yes, here. Because we have had a lot. We have had a lot of R&D work, research on this topic. We have actually developed new books. We do the traceability ourselves. We don't send it. We do it ourselves. We have airlines.
Airline, opposition airline.
Yeah, we have airlines and offset charts. And we can measure the airlines. We can measure the dimensions of the
ในเค
airlines.
เบิลแบบนี้เราก็มีในที่ดัดเราไม่ติดไปช่วยสีเสียงคือตรงเนี้ย ที่เราพูด
The cable moving to the frame before change. The why is use the quick cable. Why?
Well, because cable movement gives measure error. Yeah. So anytime you move the cable, you change something. You know, it's changing the error box. So you have to move cable only if necessary. So for one port measurements, we just keep the cable fixed. We don't move it. And for report measurements, we are very careful, you know, the way. So we have, you know, you can also see here, this is low frequency VNN, up to 3 gigahertz, very close down to 500.
For like this.
Yeah, to reduce common mount effects. We have a lot of calibration standards. To go above 67 gigahertz, you need to use extenders. You know, these are frequency multipliers.
กล่องมันเราเด็กไหม
So here you can generate up to 110 gigahertz.
It's cooling.
Yes, there's a water cooling system.
Its temperature is constant.
Yes, yes, because they get warm. And if you connect them, and draw this works. Yeah. I will show you the power measurement.
แล้วนี่ของผมอันที่เพลคาลิเบรตแล้วป่ะกับพี่อ้อ
We also have here, it's important to measure the connection. So every time somebody, you know, the customer device comes to the water, first thing is to clean the connector. You know, with alcohol. Yes, that's right. To a large extent, you can actually get rid of the cargo stress, and you have better repeatability.
What is the temperature?
It's without cooling, it would be like 37, 35 to 40 degrees, somewhere in between. But with the cooling, it's like 24.
Oh.
So this is a passive cooling, you know, it's just, here is a bank of fans, and the liquid is just, you know, being kept as close to room temperature as possible. We have some barrels with some additional thermal mass in the back.
The insulator for the temperature effect to the
This one? Yeah, well,
insulator.
yeah, it's
Heat.
it's more like to protect. This is
Thermal.
Yeah, it's more for protect. I mean, you don't want, you know, you also want to protect it a bit from external heat sources.
Actually, heat.
But the cables are not so sensitive. Here we can do it up to 67 gigahertz.
60.
But we can also.
You use it. Divide and the
What's that?
What is divide and the divide and the divide and the
DUT
What is DUT?
Oh, this is just a through connection now.
Connect.
Yeah, here is no DUT. Here, this is just to make the you know during the calibration, you need to make through connection. You know, you need to make
through
it's one of
connection.
the it's one step in the calibration is to make a through connection.
Through connection.
Yeah, exactly. But then after that, when you have done that, you can also measure a DUT, like attenuator, for example, or something else.
High accuracy or through connection.
Yeah. It just repeats and repeats.
Repeats.
But you can see it's floating,
Okay.
and so it's not, you know, the force is weak, so you don't have much stress in the connection. That's
It not be rotating.
No, it's not. It can't rotate because, well, it can rotate actually a bit because here is the center of mass, you know. But you have to be careful. You don't want to rotate too much. So this is a very delicate connector, and you have to be very careful. It's the 1 millimeter connector. The laboratory, which is a microfluorimeter. We don't have a microfluorimeter. No. But like NIST or NPL or PTB, APL. But we have some plans to become primary as well, to realize the traceability ourselves.
What type of
This is the Roder Schwartz. What do you mean? I mean, this is not finished yet. We are currently working on, extending to 110 gigahertz. But here we can do, we can provide customer calibrations up to 67 gigahertz. And we use a system which is called a direct comparison system. Maybe you heard about it. So we have, in terms of calibrations, we have the most calibration we have in S parameter and in power. But we also do some calibration in noise, and we also do some calibration in 0.23 plus minus something like that. And each laboratory has its own control. Climate control, air conditioning we have our own, so we are not connected to another laboratory, so we don't affect each other. And the power measurements are not so sensitive, but for each phenol, for each connector, and we can compare. So we don't need to send it every year. Maybe we send it every 2 years or even less, because we can compare the different standards against each other. If they don't change, then you don't need to recalibrate. If you have more standards than you need, you can actually have a monitoring of the stability of the standards. Assuming that not all are drifting in the same direction. But yeah, that's a bit unlikely. So from time to time, we send. You can put a connector underneath, and this is a device which can very accurately measure the distance between different planes in the vertical direction. And what you see here is, this is the inner conductor of coaxial connector, and this is the outer conductor of the coaxial connector, and you can see the difference. So this is the pin gap here, and here again this is the outer conductor, and you can determine here a mean value of the surface of the height. And this is the inner conductor, and you can also determine a mean value of the height. And from the difference, you know what the pin recession is, or the pin gap. We need that for our primary traceability, because in our, and that's what we have introduced new, and that's also our speciality. We have introduced, we also taking the connector into account when we characterize the standard. Not only the body of the standard, but also the connector, because the connector always has some reflection. A connector is not a smooth structure. A connector is something which has gaps and steps, and these gaps and steps, they create some reflection. So if you want to characterize the standards, the parameter standards, if you want to characterize them accurately, you also need to take these structures in the connector into account. And with this device, together with these devices, we can measure these geometries. And for the connector, with this device, we can measure these steps. But we also, we don't do all the mechanical measurements here, because at Metas we also have a dimensional laboratory, and they have very good measurement equipment. We only have here what they don't have, But you've seen in the movie the probing, and they have a very nice 3D prober, coordinate measuring machine, and there, they also do measurements of the connector. I can show you a model. You see, when we do we have a transfer stand from IPL. Use a measuring unit. And you can, if you take the connector into account, you get the red curve. That's what you expect. If you don't take the connector without connector effects, you get the black curve. But that's not what you expect, because here it goes above one. It's not possible. So this is here you can see the improvement with our method. And you see, this is how we parameterize their connector. So it's not only, here is the pin gap, this is an important parameter, but here we also characterize these chamfers and some other distances. And then we do simulations over the whole parameter space, and also to understand what the sensitivities are.
Defined through the measurement of the frequency which arises from the transition between two energy levels here of the ground state of the cesium atom. And this frequency corresponds to this 9 dot blah 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 gigahertz. And this frequency needs now to be fabricated with the utmost accuracy, and to do that, we build special atomic clocks. It's defined through the measurement of the frequency which arises from the transition between two energy levels here of the ground state of the cesium atom. And this frequency corresponds to this 9 dot blah 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 gigahertz. And this frequency needs now to be fabricated with the utmost accuracy, and to do that, we build special atomic clocks. These two laboratories, we are fabricating the Swiss time. So UTC-CH is the name of the official Swiss time, and it's really fabricated here. And just to give you a brief overview, here we have a lot of clean rules for dimensional methodology. We are measuring here extremely small pieces, and that's the reason why everything needs to be extremely clean, and that's the reason for is limited. And the reason for that is easy to understand. this is, let's say, the central part of a small atomic clock. Basically, we had here, let's say, some cesium atoms, which have been heated, and so they are moving fast. And we are selecting out of all these atoms only those who have, let's say, all the electrons, so to say, located here on the lower state here. And after that, these atoms are moving, some of them are moving this way. And what you have here is a microwave cavity. And you are coupling here inside of this cavity a microwave signal having this frequency here. And if this frequency is correct and corresponds exactly to the energy difference,
Sweeper.
yeah, not sweeping.
Not sweeping.
No, it's really, let's say, a CW frequency.
CW frequency.
Yeah, exactly at this value. And if the frequency corresponds to this difference here between these two energy levels, we will be able, let's say, to count how many of the atoms which have gone through this way have really reached this upper level. And if this number of atoms at a maximum, it means that this frequency exactly corresponds to the frequency of the transition. And this is what's happening in an atomic clock. At the very end here, we are detecting and counting, so to say, how many of the atoms are really in this upper level now. And we are trying to maximize this number by controlling the frequency of the microwave signal. And to reduce this velocity, we have to cool the atoms at very low temperatures. And so they are moving extremely slowly. And secondly, one may imagine, instead of having a short distance here, to increase this distance. And so the overall interaction time will become much larger. And so we will get much in accuracy. And this is, let's say, the fundamental ideals of the cesium primary frequency standards, the cesium fountain clocks. And this is really rapidly. And some of them are going upwards up to this region here. And in this region, we have a series of laser beams which allows to capture the atoms and to cool them down. One can cool atoms using light. And the temperature of the atoms that we can obtain here is only a few microkelvin, quite close to the absolute zero. It means that we have here some packets of cooled atoms who are moving extremely slowly. And these very slow packets of atoms are then launched vertically. It's not absolutely vertical, it's a parabolic trajectory. And we are launching the atoms this way. They are coming here up to this apogee, and they are falling down up to here. And during this parabolic trajectory, they will go through the microwave resonator. This is a little bit the same as before. We are coupling a microwave signal exactly at this 9 gigahertz frequency, and we will perform the interaction of the microwave signal with the atoms the first time here, then they are coming inside of the cavity, and a second time where they are falling down once again through the same cavity. And due to the fact that they are moving very slowly, we can massively increase the accuracy of the realization of the second.
NTP นะ NTP อ๋อนี่ใช้ meeting com
Or when comparing together primary standards, we need to measure over typically at least 1 month. So we need to measure during 1 month to reach really to the microwave cavity. You need to work in a pulsed regime. You're preparing a packet, launching it, waiting up to its falling down again, and once you have performed this operation, you can prepare a second packet. So it's really pulsed. It means that the time during which you can really measure is limited. In this fountain, due to the fact that we have this parabolic flight here, we can measure continuously without any interruption. So it allows to increase the quality of the measurement.
It's a webcam. Webcam.
It's everything in a vacuum, yes.
Cool.
10 to the minus 9 millibar.
Millibar.
Yeah, typically. Yeah, it's really a high vacuum. Just in Switzerland, which is active in that domain as well. And you have here, for example, this metal tower. This is here inside that we have the cesium atoms and that we are performing the measurement of the transition frequency by comparison to the microwave signal. This is everything here inside.
Yes, rồi. Coffee distribution em nghe như là xài ra cho nó đã.
The number is varying. But let's say maximum 8 clocks which are compared. And this scheme shows how these clocks are compared. These are phase measurements that we are carrying out. And based on that, one can really produce some kind of master clock. And these are used for the generation of UTC for Switzerland. So this is roughly speaking what we have here. Okay, so
Single frequency.
Okay.
Common view.
Okay, but it's roughly the same business. The principle is really summarized here. We are here in Switzerland, for example, and this is the station, for example, in Germany. We have our time scale here, and we are transmitting this time scale through this satellite link. So from METAS to PTV. And the German colleagues are doing the same in the opposite direction. And what we can do, both sides, is to determine the time difference between the local time scale and the time scale that we are receiving. And the difference between these two values includes some information about the time scale differences, but also information about the delay, the time delay that we have in the transmission from here to here. And we are calculating this difference here and here. And now one can calculate the half of these two differences. If we are doing that, the time delay given by the link disappears. So one really gets the information about the time difference between this clock and this one. And this is the way how everything is functioning. But we have contact, let's say, with most of the important machines. And this is what we have, for example, here in this special room. We have here different techniques. Yes, one can really calibrate watches. Reference watches which are used in the industry as a standard.
What app expert? What is
The different things that we have here. Okay. What you need to measure basically on a clock is of course the accuracy, or let's say the deviation of the time measurement. And you have different techniques to do that. For a standard mechanic, what I didn't mention, using the primary standard, the cesium Fontaine clock, we have a frequency standard available with the best possible accuracy. This model is connected to the antenna that you perhaps have seen on the roof of the building here. We have rather a big parabolic antenna, and this one allows to communicate with the satellite that we are using for these comparisons. So everything is starting from here. And yeah, that's really that. And all the computers that we have here all around allow to control this station in a fully automated way. It's really working mostly fully independent. And this is the basis for the realization of UTC, CH, and for UTC. And just for fun, which one is that? Basically this cable here, the signal that you can really hear at this very point is UTC. You are staying now here in Switzerland, or are you going back to the GNSS clock? And you can do that on one hand side, on the other hand side in the same way. And once again, building the differences, you can calculate extremely accurately the time scale difference between a clock located here and a clock located here. And this is also a technology that we are using here.
Whether you have the paper?
Yes, these are the paper clocks and the ones definitely. Yeah, that's true. Using GNSS and the precise position, point positioning techniques. Using GNSS PPP, we can compare remote clocks up to very used as transportable references. We can also perform on-site calibrations. Yeah. So this is also what we have here available.
And on, and RF is off, now RF is on. And you see, this guy immediately, let's just see. Yeah, you see all of the other signals falls out. So you see actually these here, those are the things which is with the AM modulated signal. I can go in and say subcarrier. Here and see if this one shuts down. But not really important. And then we have attenuation mode.
Automatic.
Yeah.
Normal.
Normal.
Low distortion.
You can see it in the manual because depending on the attenuation mode, you have different levels. This is only important if you're out in the fields. So if you're close to the let's see if I can.
Yeah, sideband.
Yeah. Now we. Around it, and this is the FM modulated, and the ID is quite far down. Let's go on the span.
Radio.
Take something like 20 kilohertz. It's too small. You see, it's not a fine resolution we have on this one. So, yeah, it's basically just blended. So here, this is again, you cannot display everything. It's cool here because this one with the level, if you are flying in on a certain threshold, a commercial ILS receiver will say, now I switch from chorus to chorus. So seeing exactly already from the beginning you get the spectrum displayed up here at the same time. And I get my measurements down here. Everything is spot on. This one is better calibrated than mine. Of your receiver, if I have like 95 hertz, will it still receive this? Localized antennas is much more sensitive to a thunderstorm. This one is not that sensitive. And actually the system we have here, we have 2 reference receivers and we have 1 transmitter and 1 controller. So only 1 station per airport. Not 1 per runway or anything like that. 1 per airport is enough.
ESG. So today we will focus on the calibration of how can we verify it's performing correctly. And so really the goal of before we do the actual calibration or verification, notice here, if this is symmetric, and if you know the power here, you can maintain a certain voltage or power, okay?
Okay. Yes.
Meaning this is a stable signal, and which corresponds to 0 ohm impedance. So this is a very low impedance generator, because you can control it in the loop, okay?
It's a real time.
In real time, yeah. And this, what happens is, if you can control this level in this loop, okay? It virtually you will have ground here. It's like with a fluke calibrator, for example, no? Because it maintains always the same voltage. It's the same theory. Okay? So you see, so we have the signal set to -30. So we go into the the splitter. We have it has approximately 6 dB loss. So we're measuring approximately minus 36, but plus the cable, etc. We have minus 37. Here measuring.
Okay.
Okay. And this is, let's say, this is our reference. And we'll check of the hardware. Let's say connect. Okay. Reads the software version, and depending on the software version of the instrument, there are some tests are not available. For example, it checks the options, and it checks also the autocal status. So this is the self-alignment. So if this is still valid, and then so we will do this. So you can. Let's start it. This. Report setting. You can add your name. Okay, very simple. Then let's go to this, the devices. So we need a power sensor. The power sensor.
ต้องเข้าอีกอันนึง step at 10
Level, for example, minus 10. So it's basically spot on. So it can't be much better. But so we have a loss from here to here from 6.5 dB. Okay? What it's doing later, here, it automatically, if you go to this test point, it automatically goes to minus 3 dBm. So it includes this loss already. So it's making the measurement faster. So it's not accuracy, it's just, you don't need the iteration. Okay, measurement system, we do it static. Have a, let's say, a special, so it talks to our network, and then we have this as an address, 10.120.054. So this is this. Because it was already connected yesterday, and so if I ping it, so you see, oh, no reply. Why?
No.
Huh? Yeah.
Not connected.
เจอละมี serial number ด้วย
Okay.
ที่ขึ้นข้างบน host name
And then for the step attenuator, we're using the IC or ISP, for example, if you have.
That's bad.
Okay.
Okay.
And now you have to enter the IP address of the EDS. So